we are so happy to welcome Nobel Prize Laureate in Chemistry from 2021, Professor Benjamin List.
Hey, it's great to be here with you. I'm looking forward to intense and fascinating discussions about science.
So are we. It's amazing that you take the time to do this with us. We are very, very happy for that. And we have now a room, as we can see, filled with students eager to ask you questions. And please, everyone, you can start raising your digital hands already, so that you are prepared. And when you are thinking of your first question, Professor List, you received the Chemistry Prize in 2021. If we go back in time, what brought you into science? Was that a very given path from the very beginning?
Yeah, this is very peculiar in my case, I guess. I was maybe 11 years old and I haven't even had chemistry in school already. I had physics and math, but not chemistry. And somehow I was a bit maybe a philosophical child. I wanted to understand the nature of the universe and what we are in essence and how we act in life and all these fundamental questions. And I somehow understood that the world is made of molecules and atoms and somehow I knew, I don't know where, from where, that chemists understand how molecules and atoms interact. And so I thought chemists sort of know everything. I mean, literally, I thought they're enlightened beings. No clue about the reality. And so before I knew anything about chemistry, we built our own lab. So I bought a Bunsen burner and I got chemicals from a pharmacist and we did experiments. And when I realized they don't know the answer to all these questions, it was too late. I was already hooked. And so it's been very early that I decided to become a chemist, I guess.
Do we have anyone who would like to ask a question? Yes, Parindra, please.
Thank you, Carin. My name is Parindra Kusnandoko. I'm from Indonesia. I'm currently pursuing a PhD in material science and engineering at NTNU, which primarily focus on modeling and simulation of chemical reactors as part of the development of carbon-free aluminum productions. And it's a tremendous honor to be here, and I extend my deepest gratitude to the organizers for this opportunity to engage with Professor List, whose visionary contribution, of course, have significantly shaped our field and inspired many, to including myself. So my question is, it's about the career. In your journey, actually, balancing deep specialization with a broader scope of knowledge must have been challenging. Considering my own experience for 7 years industry, where I actively navigated the balance between technical expertise and managerial responsibilities before returning to academia, I'm intrigued by how you navigated this balance in shaping your career. Did you primarily follow your inner aspiration, or were your decisions more influenced by pragmatic facts and opportunities?
Yeah, it's a very good question. This sort of navigating between, this special type of science that we do and then the big picture, right? And in my case, I think you already pointed toward it. I was always driven by sort of an inner enthusiasm for topics that came to me, kind of, and it was never based on career considerations or societal problems, to be quite honest. I always I had somehow chemistry that clicked with me and that I liked, and I pursued it. And this has changed though over the years. And I mean, Max Planck, the institution where I work, we are very fundamental science oriented, right? So this is not applied science we do here. I mean, sometimes, of course, we're very open to applied science. My institute has a great track record of very successful industrial processes. For example, the way how plastic is made was discovered here in Mülheim at my institute. And this became a 150 million ton scale process. But in general, we are sort of fundamentally science oriented. But during the COVID pandemic, we had the sort of the privilege to continue our science because we work in ventilated laboratories, right? And it was kind of safe to work here. It was kind of like working outside. And somehow the interest came to also contribute to the COVID pandemic somehow to, for example, one question that arose, can we make remdesivir? That was a very promising drug in the early days of the pandemic. We didn't have vaccines at the time, right? And so we made this molecule, the whole group worked together, and after a year or so, we developed the shortest and best route to this pharmaceutical, which, as I said, was a very promising molecule at the time. It turned out, actually, unfortunately, it wasn't such a game changer. The vaccines were. We can see Caroline Carico behind you. I can see her, and that was sort of the bigger discovery. But nonetheless, we started becoming interested in also like applied problems, and it's actually nice if we put our intelligence, our skills into solving an actual problem. And right now, in my group, we try to bring this together, like to identify problems that are really, really fundamental, and that at the same time, if we would solve them, would contribute to, a more applied problem. So this is kind of my peculiar approach that I have found for myself. For example, splitting CO2 into C and O2 is an extremely fundamental and very, very challenging chemical reaction that, to my knowledge, has not been really accomplished. But it would also, if it would be realized, potentially help us in mitigating climate change, right? And we have also contributed to the vaccines. Actually, we have a collaboration with BioNTech right now, and work on really very fascinating and peculiar problems of stereochemistry that, if we sort of solve them, could help in making the next generation vaccines, right? So this is the kind of interface where I like to be now, but it came over the years. I was always enthusiasm and curiosity driven, and I still mostly am like that. But yeah, it's a very good point.
Yeah. Thank you, Parindra. A very interesting question. Julianne, please.
First of all, thank you for taking the time to meeting with us, and I guess thank you for your scientific achievements as well. I have a question on kind of the opportunity costs of pursuing scientific research. So I guess you were maybe lucky in the beginning or had success quite early on, but there are obviously lots of projects and research topics that have a lot of failed experiments, a lot of pivots from the initial idea and thesis. And the more you have that, the opportunity costs of maybe pursuing a different research field increase. So my question is, how do you keep kind of the holistic view when pursuing your research, that you are aware that maybe you're on a wrong path and maybe it is time to pursue a different research field? Do you set yourself like a limit of failed experiments or a limit of pivots? So yeah, what is the time to maybe find a different research topic?
Oh, it's such a wonderful question, Julian. But as you pointed out, I may be the wrong person to ask, because in my case, as you said, like it was literally, I mean, it was sort of a thought experiment in the beginning. I was just thinking about it. Is it not also possible to use small organic molecules as catalysts? And it was on my mind for maybe a few weeks, like 4 weeks or so, before I actually did the experiment. But then I did the experiment, and the very first experiment on the very first day worked. And so that's why I'm not very good in giving sort of a rule how long you should pursue something where you don't know if it actually will be successful. And but in general, I would say we should really pursue something that, I mean, if you want to to do a big, or just have a big discovery or a groundbreaking achievement, right? It has to be kind of a little bit revolutionary in its nature. And that means when you do the experiment and you think about this problem, probably nobody else is. And this is something, this loneliness that comes with it, this is something I only realized lately is kind of a required condition, I would say, for a breakthrough discovery. But as the mathematician would say, it's not a, how do you say, there's a required and
Sufficient.
sufficient, exactly, thank you. The sufficient requirement, right? So because it could be a crazy idea, that's the bottom line. Maybe there's a good reason nobody else is doing this, what you dream of. And in my case, I was really nervous about what I was doing. I was thinking it could be completely naive and absurd. And I think it's our nature actually to be like this. It's our human nature is to not like to be alone. We are mammals, right? And we all want to be like together by the fireplace and sing the songs and drink and eat together. It's like this kind of loneliness is not in our genes. And then the question is really, how long do you keep up pursuing something that nobody else is? And at some point you're just, you know, an outlaw, a bit crazy. So I guess the quality of a scientist, you know, is to have not only one idea, ideally, right? So you should have more than one idea that you can pursue, and then, you know, find a good time when you know it's time to let go of a certain thing that you really were attached to and that you believed would bring the great success. I think, yeah, that's what I can say. And of course, I was so fortunate that sort of from the beginning I was successful, and then I came to Max Planck, and Max Planck is a very special funding system because I get funding basically until I retire automatically. I don't have to apply and I don't have to justify what I do. And so I can do crazy things like the CO2 splitting. Now I do it with the Nobel, of course. I can do it even openly. I say, this is the reaction I want to pursue. And if somebody tells me it's crazy, it's never going to work, okay, you know, you can have that opinion. I'm not hurt if you say that, right? And I have this funding, guaranteed funding for decades, you know, enables me to also to pursue something that's very risky and that many people think will never work. And I don't have to justify myself every year, right? So that's a very good place to be in. Yeah. So I think I would still always give the advice, go full in and take the greatest risk, even if you're not in such a comfortable environment like I am in. Go for gold and don't make compromises. Often my people here, they say, well, in the first years when they become independent and pursue a professor career, well, in the beginning I do some safe projects where I know I will get a publication out and then people know me and then I get tenure and then I can do the big experiments. But the truth is that often then what happens is they get established, and yes, they get some papers and they get, you know, some recognition for this medium level work, let's call it this way. And then they are so they become older and then that's their life all of a sudden. They find themselves in kind of a medium science world. And that's why I think go for gold and always give everything and pursue it. But of course not until the point that you're an outlaw and nobody listens to you anymore, right? So that's the balance. Yeah. Good luck.
Thank you. Great question as well. And please, everyone, grasp the opportunity now to ask questions. I'm thinking of the balance act that you're talking about, Professor List. It must be a tricky one. I'm thinking of the most recent chemistry laureate, Professor Bawendi, who speaks about an imposter syndrome that he suffers from, even though he's a Nobel Prize laureate, which is kind of a token of some success. He's still figuring out, okay, am I on the right track here, or you know?
I can completely understand him. He's a great guy. I met him actually a few years ago in Singapore, and it's sweet if we are open, because the truth is we all feel that at one or the other point in our career. I think nobody is in here and is fully confident and knows exactly what he's doing and that he will end up in Stockholm. I mean, that's the nature of what we do, right? That there's this risk of failure, right? And now actually I even like this feeling that I had back in California when I did my early experiment, this insecurity, this sleepless nights. Am I naive? Is it completely wrong what I'm doing? And for good reason, nobody else is doing it. Now I'm actually looking for this kind of feeling, right? This insecurity. It's actually a good place to be in.
That's very inspirational for everyone to hear. Thank you for that. Alina, you have a question.
What are your next ambitions after being awarded with the Nobel Prize?
Yeah, so I have to admit there was a time when, I mean, I was of course super busy actually during the last 2 years and traveled the world. I feel like I have 2 jobs, right? I have a group, I have a big department. There are 40 to 50 people in my department, and we still publish papers, and they're graduate students, they want to get a PhD. Plus, I'm Nobel Prize winner, traveling the world, giving Nobel Prize winner speeches and doing interviews like this one right now, for example. So it is very, very intense. And then you can for a while lose focus of what you actually want. But quickly I realized what I really want is what I did before, because this is my choice. I live what I always wanted to live. I do the science that I'm curious for, and I pursue my dreams, and I don't want to write philosophical books and only do this, what we're doing. I still want to do my job, right? Because that's what I love. And so yes, the Nobel Prize is there, and you could say, okay, that could conclude it, and now you can retire. But I didn't do it for the Nobel Prize, right? I did it because I like what I do, and so now I pursue even more risky things, like the CO2 splitting, for example. There's very few people, to be honest, only one in my group that are doing this together with me, and I hope that I will form a big team now that is trying to split CO2. But it gives me a big amount of freedom now, the Nobel Prize. I can really, pursue dream reactions, and there's not just the CO2 splitting. I have some other really crazy ideas that all feel like how I felt when the organocatalysis discovery was made 24 years ago. Yeah, so no, but I love to work with smart people. I have really amazing graduate students from all over the world, and just this discussing science and doing experiments. I walk through the lab, I look over their shoulders, and the joy when a discovery is made, the fun of writing a paper together, and so it's a lifestyle that I like, and the Nobel Prize is like the icing on the cake, but it's not why I'm in this.
Thank you. Franco, do you have a question?
Yes. Oh, hello, Dr. List. Deepest of respects to your work and your contributions, of course. My first question is on the context of a thesis. What is the role of the supervisor/mentor and his or her contribution to the quality of the final thesis?
The role of the supervisor, I would say, it's kind of it's a team effort, right? And the supervisor, the quality of the supervisor also depends on the quality of the student. And this interaction is kind of a give and take. The supervisor, for example, in my case, I sit in my office, but my door is always open, but I cannot make sure that I speak to everybody in the group every day and guide exactly the experiment that he does or she does, right? So, but there are some that come here maybe even every day, and just come here and have a cup of tea with me and we discuss science. And I'm very, very open and eager for that. Others are not like this. And then there's less interaction with them, and they can be equally successful if, some are just, geniuses. They don't need a supervisor. They just do their own thing. And I'm happy if I have students that have an idea that they want to pursue. I try to sort of harmonize our ideas about science, and ideally we both enjoy this, but if they're really determined to solve a certain problem that I'm not so eager on working, then I still would let them do it. And so, I mean, in my case, in my group, I still define the targets most of the time, right? I define the goals and the tools, yeah. But I know that in Max Planck and in other institutes, in other universities, the formats can be very different, right? So sometimes, you have a pyramid and you have group leaders that organize everything, that do the science for you. I could never do it this way. I love it too much, and I really want to know exactly what's happening, and I'm very hands-on with that regard.
Thank you. Johannes Elch, you have a question?
Yes, thank you. Yes, my name is Johannes. Hello, Professor List.
Hi,
Nice
Johannes.
Thank you for having the opportunity to ask a question here. I would like to ask a question about scientists and society. So I'm also from Germany, like you, and like in whole Europe, but also in Germany, like I think extreme parties are like becoming more and more votes, and and also overall, I think problems have become more complex, or I feel like they have become more complex, but people tend to try to find easy answers. And scientists or as engineers, I think we're usually like trying to untangle the very difficult questions and the complex things. And I would like to ask, how can scientists contribute maybe to society and help to make things to explain very complex things easier? Is there a way that scientists can do that, and how can they contribute to that?
Yeah, it's a good question. I think it's probably not really what drives us in the first place, right? We are curious. We want to understand the world, and we want to become scientists. That's sort of the first choice we make. But then later, if the opportunity arises, like in my case, of course, it's actually also sort of a privilege that people listen to you, right? And right now, I'm a bit worried about what's happening with the media and all these different opinions that come out and alternative facts, right? So science seems some people describe as just an opinion, right? And of course, we know also deep down, it's not 100% the truth, what we investigate. It's kind of a common opinion, a consensus often that arises, but it's not the ultimate truth. So we are inherently also not like politicians that would say this is the truth and this is a fact, right? We're more careful, and I think that's also a good thing. But speaking out and trying to educate, I think is a privilege, and it's a good thing. And for me, actually, the role I have accepted now as a Nobel Prize winner in chemistry is sort of to speak a little bit about chemical synthesis, because that's sort of my area, synthetic molecules, something where often sort of there's a reaction, ooh, there's synthetic molecules. Many people find this not very appealing, this idea that synthetic molecules are made. It sounds like very artificial and potentially toxic and so on. We're damaging the environment. And I try to carefully, I'm not pushing anybody, but try to carefully point at the benefits that synthetic molecules have brought to us. For example, like, the vaccines are not sort of biological entities that we isolate from nature. There's a lot of chemical synthesis in there. The antibiotics, the antiviral compounds, the scents, the dyes, all these great molecules. I mean, even a computer wouldn't be there without synthetic molecules and without catalysis. And I try to be sort of an advocate here for that discipline. Yeah, I don't know if that completely answers your question, but I think, yeah, it's sort of a secondary profession for us. It shouldn't be the driving force, I guess, when we go into science, right? That we want to be, I mean, that's then a different thing, like a scientific educator or so, you know. It's also important, but yeah.
Thank you. Important question indeed. Ingrid.
Hello, Professor List. Thank you for
Hi.
this amazing opportunity. My question is a bit about the bad image that is sometimes associated with chemistry regarding pollution. And
Yes.
your chemistry opens a way to greener chemistry. And
Yeah.
what is, in your opinion, the advantage in green industrial chemistry that are about to come in the upcoming years? And what is the role of a young scientist in promoting this?
Thanks. That's a very fitting question to the question that was just asked by Johannes also, and what I said before. Like this association of chemistry with environmental problems is very, very unfortunate, and I think it's inaccurate, right? The science of chemistry, sort of the chemical enterprise, is not responsible for environmental disasters or you know, pollution in the environment. That's actually human behavior, and it's typically I would maybe if at all you would complain about one of these sort of general topics of human activity, it would be capitalism that you should blame, but it's not the chemistry itself. Like plastic waste, for example, in the ocean, it's not the chemists who have designed the catalyst how to make plastic, right? It's not it's more like then what humans do with the plastic and with the waste. That's causing the problem. This is sort of what I say in general, but on the contrary, catalysis, for example, is inherently a green technology. Not only the special type that we are pursuing without metals, with organic molecules, but all types of catalysis, because the catalyst, that's the beauty of the catalytic chemical reaction. In the chemical reaction, it does not react to something else. It stays alive, and you can repeatedly use it. You can, in principle, in theory, infinitely use a catalyst to mediate a chemical reaction. So it will inherently not contribute to any environmental damage, right? But in our case, what is unique about organic catalysts, of course, is that they are inherently sustainable, because organic molecules come from nature, come from plants, and from ultimately it's kind of a materialized solar energy, if you could argue, by photosynthesis. The plants pick up the energy of the sun and then make organic molecules, sugars and amino acids and peptides and proteins and all that. And we use those as catalysts. So there is an inherent sustainability aspect about these organic molecules. But having said this, that metals are also great catalysts, and you know, there's plenty of iron, for example, on this planet, and it's a non-toxic element. And as I said, these catalysts can be recycled and reused, and they don't damage the environment much. Yeah. Well, it's a good question, and we should always, especially the chemists, we should always try to educate there, not in an aggressive way, but you know, point out to the benefits. Like, since we have antibiotics, for example, the life expectancy has enormously grown, right? And I would say that overall chemistry, like how chemistry is viewed is in the largest contrast imaginable to how actually chemistry helps humanity. So we often think it's damaging the environment and it's harming us, but in reality, actually, it's just the opposite. Yeah.
Janani?
Hi, everyone. Hello, Professor. Were there any challenges or obstacles you faced during your research journey, and how did you overcome from that?
Yeah. So I think about sort of the early days of my career when I made my discovery, and you know, there was skepticism, of course, right, in the beginning, and there were many people who would tell me like things like, okay, now you made this little discovery, but what else could come out of this idea, right? So, and yeah, people giving me advice, I should be doing something else. Or for example, they would complain about the catalyst loading. In the early days, I just mentioned the catalyst can be recycled, right? In principle, that means that one catalyst molecule is enough to make an infinite amount of new materials. But in reality, often you need more than one molecule of a catalyst, and in our case, we needed a lot. In the early days, we needed like 20 mole%. That means like one catalyst is able to make 5 new substance molecules, right? Product molecules. So that's far away from an ideal scenario. And of course, my colleagues were not hesitant in telling me all the weaknesses of our approach at the time, right? And later then, there was kind of people saying, we don't understand what we're doing fully, but I do, like this kind of thing would happen. And we are, as scientists, I don't know how you are, but for me it was very emotional. Like I'm very attached to my discovery, right? It feels like kind of a part of me. And if somebody attacks it, sometimes I wonder how it is to be an artist, right? You're on stage and you present a piano piece, and then somebody criticizes you. That must be hell. It must be really painful. In science, you can at least say, okay, this is a scientific experiment I did, and it's reproducible, and it has this kind of neutrality to it. But in reality, it's actually not neutral. And in my case, it was certainly not neutral. I was hurt when people would criticize me, but it also has encouraged me to overcome problems. For example, catalyst loading. Now a colleague of mine here, he said, I should be thankful to these people that criticized me, right? Because I was like, I want to show the world that we can be much better than that. And now we have the best, the most reactive catalysts on the planet. They are sub-part per million now, the catalyst loading, right? Not 20%, but sub-part per million. The most active catalyst. Big chemical companies are using them now in process chemistry, right? So this is how it has changed. And it came largely to the ambition here that we wanted to overcome these obstacles. So while in the moment that you face obstacles, they hurt you and they can be kind of painful, often actually, maybe even, I don't know if you could generalize this to always, but often later you find actually this was a good thing that happened to you. Some pain is pushing you into the right direction.
Thank you. Radoslav.
Hi everybody. Good afternoon, Professor List. My question to you today is: can you share with us some memorable or challenging moments from your researches or from university that shape your career approach the science and of course organocatalysis?
I mean, this first discovery, right? That was really. This is a very sweet memory for me, of course, and it was like on my mind, as I said, right? I should do this experiment. Maybe it works. I don't have to tell anybody beforehand because they might say it's a crazy idea, and so it was on my mind for a while, and then I was at the Scripps Research Institute at the time. There's a lot of chemistry, but also a lot of biology. And there was a biology lab next door. And, they grow the bacteria on agar plates. And they have to add amino acids to the agar plates to feed the bacteria. And so there was a cupboard with a huge amount of amino acids. And there was 1 kilogram of proline there. And, it was just there. So it helped me then actually really do the experiment. I went over, took this bottle of proline, sneaked out to steal their proline, and put it in my open reaction flask. Everything was sort of, I didn't need a dry box or argon or any complicated equipment. It was the simplest equipment that I had in the lab. Just a little glassware with a stir bar, and I put in proline and my reactants. And the next morning I came and we have chemists have a very easy way to already sort of see what's happening, and it's called thin layer chromatography, where you put basically a part of the reaction mixture on a plate that has silica on it, and then you have a solvent that moves by capillary forces through this plate and chromatographs, so to say, the mixture of compounds that you have in your reaction mixture. And I knew the products that I expected, and all of a sudden I saw it's there. So there was a great moment, and this has remained throughout my career. It's both the experiments that you design, like this one, it was really a rationally designed experiment. And when you see actually your idea works, that's of course extremely rewarding. But also when serendipity kicks in and something very unexpected happens, and the student comes and shows you some analytical data that is very puzzling, and something novel has formed, and you have no clue how it happened. Then the scientific part begins, and that's excitement. So, yeah, these are the moments that I cherish.
Thank you. Katie.
Good afternoon, Professor List.
Hi.
It's an honour to meet someone who I studied in my degree at university. So I think we can agree chemistry is the best scientific discipline, but what role has interdisciplinary collaboration played in your research, but also what role could it play in advancing the field of chemistry?
Yeah, that's a very good question. So when I finished my PhD, I was a hardcore chemical synthesis person. I worked on natural product synthesis and everything that has to do with chemical synthesis, organic chemistry, I had learned, I felt. And I wanted to do something else for my postdoc. And I think in general, it's a good idea. You become, like I always say to my graduate student, after your PhD, when you finish this, you should be the expert on that specific topic that you work on in the world. You should be the best. You should know everything about this field. But then it's good to open up again, take a bird's perspective on science and think where else lies my interest. And I wanted to understand how nature catalyzes chemical reactions, or how biology does chemistry, in fact, right? I wanted to learn this as ultimately somehow with this vague idea that maybe one day I find an inspiration for a renewed chemistry, for a new chemical synthesis. And it takes some courage to change discipline completely, right? And I worked with a doctor, actually, an MD, Richard Lerner. He was a virologist and immunologist, and I worked with antibodies all of a sudden, and with DNA, and I did PCR and all these things that I had no clue about before. And yeah, it's a bit, it takes courage, but I can only encourage you to pursue new things nonetheless. Because ultimately then I open up to biology. I was sort of in the world of enzymes and DNA and proteins. And then with that understanding, I went back to chemical synthesis, and this organocatalysis idea came up, right? I realized enzymes, very, very powerful catalysts in our own body and in plants and in other animals. They can have metals as the active principle, like all the chemical catalysts that previously were considered generally useful. I mean, interdisciplinarity can be extremely valuable and extremely powerful, and has been in my career. Opening up to a different discipline is a good thing, but I would still advocate to become first a specialist, right? First become really, really knowledgeable in your given area, and then open up to another one. You cannot be an interdisciplinarist from the beginning. That's what I mean, right? You have to be a specialist on one certain thing, I would say, and really go deep and know everything, and then I would say you can open up to another area.
Thank you. Johannes Hermer.
Yes, another Johannes.
Yes.
I was wondering if you reflect your career, what were like the most important decisions you've made, or were there even decisions you regret, or opportunities that you missed?
Mm-hmm. So I'm not sure if I'm the perfect person to ask this question because I was never very meticulous in planning my career moves. And I think it's something I inherited from my mom because she was pretty hands-off, a pretty hands-off mom, not like the current generation of, like my generation of parents and probably the next generation. We really try to make sure our kids go to school and they do well and so on. But my mom was not like that. She gave me pretty much all freedom you can imagine. It was a bit unimaginable nowadays, and kind of anti-authoritarian style education. That was what I enjoyed. And it sounds crazy, but this has led sort of this, but it came out of trust in her case, right? She was confident that we would be doing well. I don't know why and how, but she would always say, yeah, you will be fine. You can be anything. You can become a great composer or scientist or artist. I have no doubt. And this has then, in my case, given me a great sense of independence and freedom and confidence also, right? Because I was alone and nobody would sort of check on me much. I was free and I made my decision often very intuitive and just like, for example, how did I find the Freie University in Berlin where I studied chemistry? At the time there was no internet, so that's the first thing. So I had no clue about the university landscape in my country, but I wanted to study in Berlin. And so I called the operator. At the time, you had a stationary phone. I don't know if you remember this, you could dial. And I called the operator and said, can you please give me the phone number of the University of Berlin? And then the lady said, yeah, but which one? And I said, oh, there are more than one. And then she said, yeah. And I said, okay, you pick one. And she picked it, and it was the Freie University. And it was in hindsight, it was a wonderful decision that she made for me. It's a really beautiful university campus in the south of Berlin, very peaceful, very nice neighborhood. And I enjoyed it, and I stumbled into great teachers. And then later, the decision to go to Scripps was I met a guy on a conference, and he said, I heard about this catalytic antibody field, pretty interesting. And then, I began researching it, and I thought, this could be something for me. And yeah, I took great risks also at times in hindsight. Like I was kind of a bit naive and always sort of confident somehow, something will come up and I will solve a big problem and I will make a career. Somehow I didn't really listen much to advice. My auntie, she's also a famous scientist, she would tell me things and I would just do the opposite, So I don't know, I guess there is kind of a message that I can give in it that's really, trust your own intuition and your own ideas and don't listen too much to any advice, even to my advice. Like, do what you really want to do. Do what you're passionate about, what you're enthusiastic about. That will be your guiding light. Of course, others will tell you different things. You should go to the best school, get the best diploma, and then I don't know, study informatics because that's the future or stuff like this. But yeah, I wouldn't follow that fully. I would say, rather go for what you really love to do. This is the best recipe actually in general. The best advice you can get is because ultimately, I mean, what's the definition of happiness? I would say it's when you do what you really love to do, right? You're happy. There's no complaint. And now imagine this is your job. Right? You like in my case, I love this kind of science catalysis. It's always magic and so beautiful and so powerful and enabling. And it happens also to be a technology, right? So it's just so rewarding to be in this field. And then, you don't have to think about how to make money or how to, live a life if you just follow your enthusiasm. I think there's nothing that can go wrong, basically.
Great advice. Julianne, please.
Felt like this was kind of the perfect closing statement, but if you don't mind, one other question, I would like to piggyback on what Katie just asked in terms of collaboration when it comes to scientific research, and maybe more on a macro view. Do you think in the future we have like open, decentralized, and collaborative research, or will there be like an arms race between governments because they see the value of scientific achievements and deep tech maybe to create like domestic value? I hope you say like the former one, but what's your opinion on the macro level of scientific collaboration?
It's beautiful that you asked this question, Julian. I don't hear this a lot where people think about a different style of science, right? In a way, it's kind of awkward that we still operate like several hundred years ago, right? We do it confidentially and very competitively. And for example, in a field, protein crystallography, people discover the structure of a protein. This is one of the most intensely competitive area in biology and structural chemistry. But they all do the same thing on different places in the world. And then, maybe by chance, by luck, somebody gets the structure, they get the Nature paper, they go to Stockholm, and this is how this operates. But in maybe, I sometimes wonder, maybe future brings a different type of science, an open science where we're not driven by egos and wanting to get the recognition, I was the one discovering it, but where we are more like collaborative, trying to solve problems. I think this could be extremely powerful. I believe in a smart crowd intelligence, for example, not in sort of the crowd itself, but a smart crowd intelligence. For example, we have established a new peer reviewing mechanism with the journal that I have been an editor, and it's different than we used to do it in the past. Like we would send out a manuscript to 3 or 4 referees, and they would then write the letters, and then the editor would get the referee response back and make a decision. What we do is we put the manuscript kind of online in a secured platform, and then many referees at the same time can see it and discuss the manuscript. So that also has sort of a corrective factor with it. So, for example, a referee might write something wrong, and then another referee will correct it, right? So this is much more powerful, and also, of course, much faster than the traditional peer reviewing. And I also wonder sometimes, could there be a science where we just have an open lab journal? Like all the experiments we do are online right away when we do them, right? Would this not be better for humanity as such? I don't know. And then others say for science, actually, this competitiveness is good about it, right? Because people are really motivated to win the big award and to make money and so on. I don't know, but I hope and I imagine humanity to grow in such a way that we are just openly and not ego-driven, but driven by the betterment of the planet and the life of all beings on this planet.
Yeah. That would be a good thing, indeed. Katie, the last question.
No pressure to make it a good one. What emerging areas of research do you find particularly exciting for the future of chemistry? Or like what areas should we be keeping an eye on?
In chemistry?
Yeah. I mean, science as a whole, if you want.
Yeah, I think for me, I don't know, I'm a bit surprised that not many more people have identified the CO2 problem as a chemical problem, right? It's a great problem. CO2 is a very unreactive molecule, but it's also an organic molecule, and it's not completely unreactive, right? You can use it as a starting material for chemistry. And it's such a great thing because it's a fundamentally challenging scientific problem to activate a very unreactive molecule. And the chemistry of CO2 is not really well explored. And again, what I said before, it comes with this beauty of potentially solving a big problem of this planet right now. Imagine we could take on scale CO2 out of the atmosphere and convert it into something useful that is sort of storable. We could solve climate change, right? And not only that, potentially with the carbon material that we take out of the atmosphere, we could also solve the transformation of the chemical industry away from sort of fossil material into the most renewable material there is, CO2, right? We could basically, chemists could convert CO2 into everything, into all of chemistry, together with sunlight and water perhaps. And so, plus if you make like energy-rich materials like coal, this is sort of my dream reaction, CO2 to O2 and C, you also solve the energy problem, right? I mean, there's so much potential in this, and I don't know if in my life we will be very successful in contributing to this, but I will definitely try with my team that is slowly growing. But I can only encourage everybody in the world of chemistry, the next generation, to address this problem. There's a lot of fundamental science, but also, you know, potential solutions to big problems of humanity.
What a great end, filled with hope, indeed, and possible solutions to our challenges. I want to thank you all for your amazing questions, and Professor List for your very enlightening and inspiring answers.
Thank you. It was really, I always enjoy this interaction, and there were incredibly inspiring and smart questions. I see a lot of geniuses here. Maybe we meet again one day in Stockholm, who knows, when I'm a guest and you will be honored. I know. I see great talent here, and it was really a delight to discuss with you.
Thank you.
Bye.
Bye.